Okay, so guys, we're talking about number five in here, and we're talking about Newton's law of cooling, right? So it says when an object cools down, we can implement an exponential decay model, but we have to add a few alterations. This gives us the formula known as Newton's law of cooling. So the formula itself is actually extremely similar, right? It's just that we need a couple of changes because if you guys look at our if you look at our normal exponential growth model, right? Boom, right
Mhm.
here. What value is it going to? Like, what's the end behavior of this?
Always zero, actually,
If
isn't
it
it?
was a decay, I mean, sorry, if it was a decay, like in this problem here, it goes
It
towards
would be.
zero, like
All
you
right.
say.
Yeah.
No, no, thank you. It goes towards zero, right? So,
Yeah.
what's going to happen is when you're talking about an object cooling, it doesn't actually necessarily go to zero, right? What happens is it cools to, I mean, if you have something just sitting in room, it cools to room temperature. Or if you put a hot object in water, it cools to whatever temperature the water is, right? Um, so what this does is it changes things a little bit. It's going to make it so that the lowest our coffee can cool to is the room temperature that she's within. Um, but so, sorry, I'm getting ahead of myself. Let's talk about this a little bit. So in part A, it says think. Why does the coffee cool down over time, right?
Because all the energy is being released into the atmosphere. So even though it's cooling down, the temperature inside the room actually warms up because it's absorbing it.
Hmm. Yeah, exactly, right. The heat of the coffee is dissipating, right, into the room. And what's going to happen is actually, if we look at it like, if we think about it as like, what's it called? If we think about it as, let me just switch to my whiteboard so that we can write while we're talking about this. If we think about it, guys, you have this hot coffee, right? That's the steam from the coffee mug, right? That's the heat escaping, right?
Yes.
Now, in a room, there's no way this coffee is going to make the room hotter, right? So all we have to worry about is what temperature is it outside. The coffee itself is 93 degrees Celsius, right? The room
Yes.
outside is 20 degrees Celsius. What's going to happen is if we sketch a graph of this over time, the coffee is going to go from our initial value of 93, right? It's going to cool down, but that cooling will peter off as it gets closer and closer to 20 degrees Celsius,
20
creating
degrees Celsius being our end behavior.
exactly
Yay.
creating our end behavior a horizontal asymptote. So do you see how this graph here kind of models what the temperature is going to look like over time, right? Um, and and eventually there'll be some point where the coffee has actually reached 20 degrees Celsius, but that's actually something unusual for math, right? Usually in math, in our mathematical model, this is going to go off forever and never actually quite reach 20, right? But I mean, in real life, there is some time where it'll reach 20. This is one of the limitations of modeling, right? But it's okay because we get close enough to where it doesn't really matter, right?
It's a
So,
hue stick. It's just an approximation.
yeah. So, what we're going to do is we're going to talk about how this all relates to Newton's law of cooling. So to do that, we need to first kind of take a little screenshot of the next section, maybe post that in here, expand it a little bit, and let's talk about this, right? So guys, this is Newton's law of cooling right here. T of T equals T sub m plus T sub naught minus T sub m e to the RT. That's a big mathy, super math, like using these subtexts is super mathy, right? But it's okay, guys. We can break it down. The idea is that T of T, right? That's the temperature over time, right? So our model is measuring the temperature of some object as it cools down over time, right? T,
See.
T sub m is the temperature of the medium. The medium is just whatever the coffee is surrounded by. So in the case of this problem, it's the room itself, right? Um, Another example of something of that sort, right? Suppose I had when people are blacksmithing, they have a hot, they have like the hot metal that they just worked, right? But then they put it into a cold bucket of water. And what happens is the metal releases its heat into the water, right? So the water is the medium. So the medium can be anything that our hot object is surrounded by, which is cooler. Okay. Finally, we have T sub naught. That's the starting temperature, right? Whatever temperature our hot object is starting at, right? So you can see that in order to get this horizontal asymptote to not be 0, this is why we're adding the temperature of the medium, because it's the lowest our temperature can get. Okay. Then, because because our end behavior is up here at 20, we need to take our starting value and subtract that exact same value of the medium, because we don't care actually about what the temperature is that we're starting at. We care about how much greater are we starting at, right? So you can see we're doing a difference. Okay. I'm gonna pause a second. Just do we have any questions about that?
Easy win.
Cool. Okay. So now, yeah, this formula looks crazy, right? It's a little bit intimidating, but it will actually work extremely similar to what we were doing before. Okay, guys. So, uh, here we said Nikumi decides to let the coffee cool because she doesn't want to burn her mouth, right? So she wants to wait until the coffee has reached 55 degrees Celsius. So our goal is 55 degrees Celsius. All right, that's going to come in later. When she does a temperature test of the coffee, she detects that the coffee is oop, oop, 65 after 7 minutes. So it took 7 minutes for the coffee to cool down. Now the reason why that matters, guys, is because different objects cool at different rates, right? So this is why we can't all. This is why we need to calculate growth rates. Okay. So let's go ahead and start plugging these things in. Uh, what is our initial temperature that we're working with, right? What's T sub naught going to be? What was the initial temperature of the
93,
coffee?
right?
Yeah, the coffee was originally 93 degrees Celsius, right? 93 degrees Celsius. So our T sub naught is going to be 93. Oh, let me use the black. We don't need 93. Now, the temperature of the medium was 20 degrees Celsius, right? So for T sub m, we're going to plug 20 in. So we have 93 minus 20, and we also are adding 20 over on this side. And then we look at the rest of it, right? We have e to the rt. E is just a constant, right? So we just throw it in there. We do not know r because we're going to calculate it. And then here's where t and t of t need to come in, right? This is why she does a temperature check. If you do a temperature check at some later value, then it allows us to calculate the growth rate, right? So we know that after 7 minutes, it was 65 degrees Celsius. So our time, right, t, little t, our time is 7 minutes. So we plug 7 in here for time. And the temperature at 7 minutes is 65 degrees Celsius. So this equals 65 degrees. At this point in time, guys, solving this model is just like all the other problems we've been doing, just with a little bit more steps, right? What I want to do is go ahead and give you guys some time to try solving this yourselves. And for those of y'all watching the video of this, I'm actually going to stop the video because I want you to solve this yourself for the growth rate. If you need any help with solving this, you're always welcome to message us on Discord or go check out some of the other video that I'm going to post here where we do solve an equation just like this. Okay? All right.
Yeah. Thanks, Ova.
Bye bye.
You smell